Okay, 11.2, part 2. This, like I said, it was a long section, so I broke it into two parts, trying to keep them around 15 minutes. Telescoping series is another type of series like geometric. It's easy and quick to find to the sum, but you got to see the pattern. So here we are going to take both these and list out some possible factors. All right, it's not geometric. We're going to look for partial sum patterns. So my first term when n is 1 over 1 is 1, minus 1 over 1 plus 1, which is 2. So when n is equal to 2, our next term would be plus now 1 over 2 minus 1 over 2 plus 1, 3. Here's the pattern. I keep adding 1 to each one of those individual fractions in these binomial terms. So plus 1/3 minus 1/4 plus 1/4 minus 1/5 plus all the way out to 1 over n minus 1 over n plus 1. Well, hopefully you saw a pattern right away. Minus 1/2 plus 1/2. Those are going to cancel. Minus 1/3 plus 1/3. Those are going to cancel. Minus 1/4 plus 1/4. They're going to cancel. So the minus 1/5 will cancel with a positive 1/5 somewhere. And the minus 1 over n will cancel with the 1 over n. And we're left with 1 minus 1 over n plus 1. So here, taking an infinite series and writing it as a finite series, we can shorten it down, but what we're going to have to do to make go back to infinite is we're going to have to take the limit of this, if you will, sequence function series that has been simplified and take the limit as n goes to infinity. So the limit as n goes to infinity of 1 is 1. We've seen this before. 1 over infinity, that's a 0. So 1 minus 0 is 1. So we found the sum. Okay, so this series converges and its sum of that series is 1. All right, example 9. Here, we can't work with this fraction here because we need a minus of two fractions like we had in the previous example to get this cancellation to happen to make it a telescoping series. Telescoping is because everything on the inside cancels out when you're left with the beginning and the end. So we need to do a partial fraction decomposition to find out what two fractions were being added or subtracted together. So here we go, 1 over n times n plus 2, capital A over n plus capital B over n plus 2. All right, let's multiply by the least common denominator right there. We're going to get a times n plus 2 in parentheses plus bn, and that's all equal to 1. All right, so let's cancel. Let's let n be 0, so that's going to cancel out the b term. So 0 plus 2 is 2, so 2a equals 1 means a is equal to 1/2. Do the same thing. Let's let n be negative 2. So we can cancel out that binomial there. So this is a 0. And we get negative minus 2b. Divide over the negative 2, b equals negative 1/2. So this one fraction here now becomes 1/2 over n instead of plus minus 1/2 over n plus 2. Okay, well, let's factor out the 1/2 out to the front of the summation. And now we have this looking like our previous problem. Let's start finding some terms. So when n is equal to 1, you're going to have 1/2 times, here comes the series, 1 over 1 minus 1 over 1 plus 2 with 3. So you can see the pattern. I'm going to keep again adding 1 to each denominator. So plus 1/2 minus 1/4 plus 1/3 minus 1/5 plus 1/4 minus 1/6 plus 1/5 minus 1/7 plus 1/6 minus 1/8, and on and on and on. And then we got to start from the back end when our n is going to be n. So we're going to start with our sequence function here, plus 1 over n minus 1 over n plus 2, close the bracket. But now we got to find these terms going to the left, and now you have to, instead of add 1 to the denominator, you have to subtract 1. So n minus 1 will be n minus 1. N plus 2 minus 1, well, that'll be just n plus 1. The next one, subtract another 1, that'll be n minus 2. And subtract 1 from 1, that will just be n. So 1 over n minus 2 minus 1 over n. Okay, subtract 1 again. N minus 3, n minus 1 as my denominators. Everything else stays the same. 1 over n minus 4 minus 1 over n minus 2. Subtract 1 from the 3, minus 3, and subtract 1 from the minus 1. We get minus 4 minus 2. Let's start looking for terms to cancel. Minus 1/3. I thought I saw plus 1/3. There they are. They cancel. No, all I see is a plus 1/2. So I'm going to go to the minus 1/4 plus 1/4. They cancel. Minus 1/5 plus 1/5 cancel. Minus 1/6 plus 1/6 cancel. Notice that, hey, in those two binomials right there, all my terms cancel. They're going to keep canceling all the way out to the end here. But we did have some leftovers at the beginning, so that means there's going to be some leftovers at the end. Oh, let's see. 1 over n minus 1 over n. Those are going to cancel. Oh, going back here, the minus 1/8, minus 1/7, they're going to find something to cancel with. Those are going to cancel. Minus 1 over n plus 1. I don't see any other n plus 1, so let's look at n minus 1. Here's an n minus 1, minus, plus. Those two cancel. N minus 2 plus, n minus 2 with a minus fraction. Those two cancel. And just like with the minus 1/7 and the minus 1/8, those found someone to cancel with. So will the 1 over n minus 3 and the 1 over n minus 4. They'll find someone to cancel. So we have the 1/2 times 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. So we'll take this and now apply the limit as n approaches infinity. Well, you can see what's going to happen. These two fractions right here, bigger on the bottom, top stays the same, approaches 0, approaches 0. So we have 1/2 times 1 plus 1/2 is 3/2, multiplied together is 3/4. So therefore, that infinite summation for 1 over n times n plus 2 will converge, and its sum of that series is 3/4. All right, theorem 6. If the series as n starts from 1 to infinity for a summation of a sub n is convergent, that means we know it's going to come to some value, then we know that the limit of that original sequence is going to have to be a 0, because we're not going to be able to add on any more values to it. So as you saw in the last example, we had two fractions that converged to 0. Okay. However, if you read this in reverse, backwards, called the converse, it's not true. If the limit as n approaches infinity of a sub n equals 0, so if the limit of this is going to equal 0, we can't conclude that it converges. There are some cases where it will also diverge. But what this does is that it gives us a good test for divergence. So if the limit as n approaches infinity of a sub n does not exist, so we're looking at what are the only other things that can happen besides the limit of a sub n equaling 0? Well, the limit doesn't exist, or the limit equals something other than a 0. If that happens, then we know the series, that infinite series of a sub n, is going to diverge somewhere. Okay, so if the limit doesn't exist, say it's going to infinity, then it's divergent. Its sum's going to infinity. All right, if the limit doesn't equal a 0, then it's going to be divergent as well. Okay, so from previous examples, here's our infinite series that it was divergent. Notice here, you take the limit of your sequence function as n goes to infinity, that's infinity. So it does not exist, so it diverges. So here, 1 over 2 to the n power, this limit was a 0. Now this may converge or diverge. Now we saw that it actually did converge, but again, we're not sure of which one. All right, so here's an example 10. Let's find the limit of our sequence function. Well, wait a minute, that's a rational function. We can use your horizontal asymptote rule here. They're both raised to the first power, so 4/3 is your limit. But that doesn't equal 0. That means this converges. All right, again, if you think about the limit, think about your values here. Where is my sum actually going? The top is always getting bigger than the bottom, so it's always going to have a little bit more to add. So I'm going to keep adding on more values, so the sum's just going to constantly get bigger. It's not going to get smaller. So this diverges. Okay, theorem 8, this is where we can use some of our summation properties and use them for converging series. So all these properties you saw in the past, we can use them again. So here, with this example, the summation of n equals 1 to infinity, we probably want to break this function into two fractions and therefore rewrite it as two summations. So break it into two fractions, 1 over 3 to the n plus 2n over 3 to the n. Then rewrite them as two summations. I'll have first one will be blue, second one will be red. So I have 1/3 to the n power and 2/3 to the n power. Wait a minute, these are two geometric series here. So therefore I know they both converge. So find the sum of this one, find the sum of that, and we add it together. We have the sum of our example summation. So using your infinite sum formula, a sub 1 over 1 minus r, let's see, got to plug in a 1. 1/3 to the first is 1/3. That's your first term. 1 minus r, that's going to give me 2/3. So 1/3 over 2/3 is a half, or you can multiply top and bottom by 3 and get 1 over 3 minus 1 to get 1/2. 6 and 1/2 dozen the other. For the red, plug in the 1, 2/3 to the first, that's your first term. 1 minus r 2/3, that's going to be 2/3 over 1/3, which is 2, or again, multiply top and bottom by 3. You get 2 over 3 minus 2, which is 2. Add those together, we get 5/2. Oops. All right, so the finite number of terms doesn't affect the convergence or divergence of a series. For instance, suppose that we were able to show that the series, say it started at n equals 4 to infinity of n over n cubed plus 1, it's convergent. Well, since n equals 1 to infinity of the same sequence function would be 1/2 plus 2/9 plus 3/8 plus, okay, there's the rest of our terms, which is up here. So it follows that this series, if we started at 1 for n, it too will be convergent. All right, similar if it is known that the series is bigger, has more terms, and we want to take off a few terms, then that smaller function would also be convergent.